Welcome to Module 9. In this module, we apply the concept of the derivative to the behavior of a function. There are a few concepts that we need to get out of the way first. Higher-order derivatives. A higher-order derivative refers to the process of taking derivatives of derivatives. For example, say that we have the function f of x equals 2x to the fourth plus 5x minus 3. The first derivative is f prime of x, which equals 8x cubed plus 5. Now, if we find the derivative of this function, we arrive at the second derivative, f double prime of x equals 24x squared. It is possible to find the third or fourth derivatives or even higher ones, but the first and second ones are generally sufficient for most applications. Increasing and decreasing. When we calculate the first derivative, we find the instantaneous rate at which the function changes. This function is increasing whenever the first derivative is positive, and it is decreasing whenever the first derivative is negative. To identify points where the graph transitions from increasing to decreasing, or vice versa, we look for where the first derivative equals 0. Concavity. The second derivative finds the rate at which the first derivative changes. When the second derivative is positive, we say that the graph of the function is concave up, often described colloquially as regions where the graph smiles. If the second derivative is negative, then the graph is concave down, corresponding to regions where the graph frowns. So in regions where the graph is concave up, the way that the function is changing, whether increasing or decreasing, is speeding up. In regions where the graph is concave down, the way that the function is changing is slowing down. Consider this function. At the point -3, -16, we observe that the function is on the rise, since the slope of the tangent line at this point is positive. The function is also increasing at the point 2, 4. So the first derivative at this point is also positive. However, the way that the function increases at these 2 points differ. At -3, -16, the function is concave down, resembling a frown. So the second derivative at this point is negative. And although the function is increasing here, the rate of that increase is slowing down. On the other hand, at 2, 4, the function is concave up, resembling a smile. So the second derivative at this point is positive. The function at this point isn't just increasing, it's doing so at an accelerated rate. One last analogy about the second derivative. Imagine that you are driving a car along a stretch of highway. Throughout your journey, you're moving forward, meaning that the distance increases as time passes. In this scenario, the first derivative of your position is positive, indicating that you're advancing forward. However, during your drive, there will be moments when you accelerate to go faster or decelerate to slow down. These changes in your speed relate to the second derivative. When you accelerate, the second derivative is positive, showing that your speed is increasing over time. On the other hand, when you decelerate, the second derivative is negative, indicating that your speed is decreasing. Let's jump into some examples. Okay, so in example 1, we have a software development project, and the productivity ratio is modeled by f of x equals 100 over x plus 1. Here, x is the cumulative number of hours since the project began. Okay, so in part A, we're looking to see what is the productivity ratio when x equals 9. Now the productivity ratio is given to us by f of x, so we're just looking for f of 9. Now we have f of x is equal to 100 over x plus 1, which means that f of 9 is 100 over 9 plus 1, which is 100 over 10, which is just equal to 10. And so what we know is that the productivity ratio when x equals 9 is 10. Now let's remember what this means. This means that on the graph of f of x, we have the point 9, 10. Now, in part B, we want to know, is the productivity ratio increasing or decreasing when x equals 9? And we know that increasing and decreasing comes from the first derivative. So I need to find the first derivative. I'm going to start by rewriting the function. Now, I'm not taking the derivative yet, all I'm doing is rewriting the function. And I know that this is equal to 100 times x plus 1 raised to the negative 1. And now I'm going to take the derivative of this, which I know is f prime of x equals negative 100 times x plus 1 raised to the negative 2. Now at this point I would take the derivative of the inside and multiply, but the derivative inside of here is just equal to 1. So my derivative here is negative 100, and I'm going to bring the x plus 1 to the negative 2 downstairs. And so we get negative 100 over x plus 1 quantity squared. So I need to know, is the productivity ratio increasing or decreasing when x equals 9? Well, that would just be f prime of 9, which is negative 100 over 9 plus 1 quantity squared, which equals negative 100 over 10 squared, which is negative 100 over 100, or negative 1. And because this is negative, we know that the productivity ratio is decreasing at x equals 9. Well, now in part C, we want to know, is the rate of decrease speeding up or slowing down? So I need the second derivative. To find the second derivative of f of x, I'm going to look back here at the first derivative. And we see when we bring the negative 2 out in front, we get 200 times x plus 1. We subtract the exponent by 1 to get negative 3. And again, we would multiply by the derivative on the inside, but that's just equal to 1. So we have 200 over x plus 1 quantity cubed. Now I see that f double prime of 9 is equal to 200 over 9 plus 1 quantity cubed, which equals 200 over, let's see, 9 plus 1 is just 10, and when we cube that, we end up with 1,000. And so 200 over 1,000, we can rewrite that as 0.2. So what I know here is that the rate of decrease is speeding up. In other words, the decrease is happening at an increasing rate. In this example, we have a telecommunications system where the signal strength measured in decibels varies over a period of time. The strength is modeled by f of x equals negative 3 times sine of 0.5x minus 2x minus 40. Here x represents time in hours. In part A, we want to know what is the signal strength when x equals pi over 2. Well, that just means that we need to find f of pi over 2. And so we plug pi over 2 into f of x. We have negative 3 times sine 0.5 times pi over 2 minus 2 times pi over 2 minus 40. Now at this point, I'm just going to plug this into my calculator and see what we get. Looks like we get something approximately like negative 45.26. In part B, we want to know, is the signal strength increasing or decreasing when x equals pi over 2? Now we know that increasing and decreasing comes from the first derivative, so we need to find the derivative of f of x. Alright, so we have f prime of x is equal to, and I'm just going to write down this negative 3, and we see that we have a function inside of another function. Now the outside function is sine. And we know the derivative of sine is cosine. So we're going to have cosine of 0.5x. And now we need to multiply by the derivative of the inside, which is 0.5x. And the derivative there is 0.5. We also have negative 2x, so when we take the derivative there, we just get negative 2. And the derivative of negative 40 is just 0. Now to find whether the signal strength is increasing or decreasing when x equals pi over 2, we just need to find f prime of pi over 2. And again, plugging this into our calculator, we find that f prime of pi over 2 is approximately negative 3.06. So it seems that the signal strength is decreasing at pi over 2. Now in part C, we want to know, is the change in signal strength speeding up or slowing down when x equals pi over 2? Well, that means we need to find the second derivative. Now before we jump into the second derivative, I think I'm just going to clean up the first derivative a bit here. Now the first derivative is equal to negative 3 times cosine 0.5x times 0.5. And the 0.5 times negative 3 gives me negative 1.5 times cosine 0.5x. And we subtract 2 from that. And so now I'm ready to find the second derivative. We have f double prime of x is equal to, and let's go ahead and write down this negative 1.5. And again, we have a function inside of a function. And so the derivative of the outside function is going to give us negative sine times 0.5x, and the derivative of the inside will be 0.5, so we multiply by 0.5. And the derivative of negative 2 is just 0. Now let's see, we have negative 1.5 times a negative times 0.5, and that's going to give us 0.75 times sine of 0.5x. And so to find whether the change in signal strength is speeding up or slowing down when x equals pi over 2, we just need to find f double prime of pi over 2. And plugging this into our calculator, we find that the second derivative at pi over 2 is approximately 0.53. And since this is positive, we know that the change in signal strength is speeding up. In this example, we have a data center, and the efficiency of a server cooling system at temperature X in Fahrenheit is modeled by f of x equals negative 0.11x squared plus 13.64x minus 323.84. And this is good for temperatures between 32 and 92. We want to find each of the following. In part A, we want to know the temperatures for which the efficiency is increasing and decreasing. And we know that increasing and decreasing comes from the first derivative. So we find the first derivative. So we have negative 0.22x plus 13.64. Now we want to know where the function is increasing and decreasing. In other words, we want to know where this derivative is positive and negative. So I'm going to start by just setting this equal to 0. And so I have negative 0.22x plus 13.64 equals 0. And that implies that negative 0.22x equals negative 13.64. Well, this means that x is equal to negative 13.64 divided by negative 0.22. And this gives us 62. So I need to know, is f prime of x positive or negative both to the left and to the right of 62? And I think what I'm going to do here is I'm going to make myself a little sign chart. And at 62, I know that the derivative is equal to 0. So let's remember that what I'm putting up here deals with f prime of x. And so I need to know, where is f prime of x positive and where is it negative? We know it's 0 at 62, but if we look at what's happening to the left of 62, and we're going to go up here and check to see what do we get when we plug something like that into f prime. I'll choose some number over here, like something like 40. And when I plug 40 into f prime, we see that it's positive. And so I'm going to put some little plus signs here to indicate that the derivative is positive to the left of 62. Now let's do the same type of thing to the right of 62. I'll choose some number here, like maybe 70, and I'll plug this back into f prime. And when I do that, I find that the first derivative is negative when we choose numbers to the right of 62. Now if we just look at our sign chart, we see that it's telling us where the derivative is positive and where it's negative. So we know that f prime of x is positive to the left of 62, meaning that the function is increasing there, and it's decreasing when x is greater than 62. Now in part B, we want to find the optimal temperature for system efficiency, and we can just look back at our sign chart. We see that if we choose some temperature that is less than 62, there's still improvements that could be made, because the derivative is positive there. On the other hand, if we choose a number that is greater than 62, then the efficiency is decreasing there. So it looks like the optimal temperature here is at 62. In part C, we want to find the temperatures for which the function is concave up and concave down. Now for that, we need to find the second derivative. Now when we look back up at f prime of x, we can pretty easily see that the second derivative here is just negative 0.22. And negative 0.22 is negative no matter what x is. In other words, when we look to see where this is concave up, well, it's never concave up. And where it's concave down, it's always concave down. Another way of saying this is that for no temperatures is the function concave up, and for all temperatures, the function is concave down. Before we wrap up this module, let's explore a practical application of second derivatives as they are used in the real world, specifically in the field of image processing. A key task in the area is edge detection, which is crucial for identifying the boundaries that separate distinct objects within an image. Edges in an image are defined by sharp changes in pixel intensity, the individual points of light that compose the picture. Imagine that we have an image, and we decided to examine a horizontal line across this image. As we move along this line, we measure and graph the luminosity, or brightness, of each pixel we encounter. Looking closely at this graph, we notice something interesting about the edges of the objects within the image. The edge is marked by a significant shift in luminosity values. To understand this through calculus, we look at the first derivative of the luminosity profile. Initially, the luminosity values change little, indicating a flat or nearly flat section of the graph, which in turn means little change in luminosity. However, upon reaching an edge, there's a stark decrease in luminosity, reflected in the first derivative graph as a steep, negative slope before it stabilizes again to relatively constant values. Taking this a step further, let's consider the rate at which this first derivative changes, which brings us to the second derivative. This rate remains minimal until we hit the edge, where there's a rapid decrease followed by an increase in the derivative values. Therefore, we can detect an edge at the point where the second derivative crosses zero, characterized by a significant difference in its values immediately to its left and right. This method allows us to pinpoint edges with an image with precision, showcasing the power of second derivatives in analyzing and processing visual data. It's time to wrap up this module. Here, we've explored how derivatives influence graphical properties. Moving forward, we shift to antiderivatives, aiming to reconstruct functions from their derivatives. This transition will deepen our understanding of calculus and unlock new insights into its applications.